All right. I'm going to talk to the computer for a minute. Keep working. If you're watching this at home, come up with a reaction for this mechanism or a mechanism for this reaction. And I'm going to hit pause in just a second. And then when you have the mechanism start up. All right. So, if you're grading this, so now I want you to write your name at the bottom. So this is if you grade it and you put anything on there, like you put a jerk or distance. Okay, so yeah, I wasn't terribly clear about this, I guess. You need an acid for this process. Actually, you can do this with base as well because it winds up in hemiacetal. But I've put in an acid. So this P is para, TS is tosylate. So you guys might remember tosylate from Orgo 1, and OH is just the acid. So right, this bit here, the benzene bit with a methyl, that's toluene. Right, so a benzene molecule with one methyl ion is toluene. That's a really common organic solvent. If you wind up working in the chemical industry at all, if you wind up working anywhere where chemicals are handled, toluene is one you really might encounter. And then this is a sulfonic acid. So this is sort of an organic equivalent of sulfuric acid. Right, so sulfuric acid is that H2SO4. And I think most of you come into this class knowing that sulfuric acid is H2SO4, but you just see it written that way. Sulfuric acid has a Lewis structure, it's that, right? The SO3H part is just like that. By replacing this OH with a toluene, we make that molecule more organic soluble. Right? We can't really dissolve sulfuric acid in an organic solvent. So if I have hexane and I put a couple of drops of sulfuric acid in, I'm just going to get two phases. But if I have an organic solvent and I use paratoluene sulfonic acid, all of a sudden I have a strong acid that can go into this. It can be dissolved in the solvent. Paratoluene sulfonic acid is a little less acidic than sulfuric acid, right? Being a little less acidic than sulfuric acid makes you can still be a really strong acid for that. So this is our acid source. The other thing I want to make sure hammer. Okay, so if you're going to use an acid, and if you're going to protonate something in a solution, the thing that's going to supply the proton is the strongest acid. If I have a mix of 12 chemicals and I put a base in, if that base takes a proton from something, it's going to take it first from the strongest acid. If it consumes all that, it'll take it from the next strongest acid, and so on and so forth. Same thing is true in reverse. If something's going to take a proton, it's going to be the strongest base. I see this error. I mean, I tried here by not putting anything, right? There's one reagent. So there's nothing, you don't have to choose what does the protonating. But I see this a lot when I put H3O plus in water. People will use the proton from water and they'll make hydroxide. And I think maybe a lot of you don't actually think that through. You're like, draw the arrow to the H because you know you got to protonate something. And you protonate. You're like, you get the correct thing protonated, but you don't follow through that OH minus has to come off the other side. All right, so you've basically made a strong base in the presence of a strong acid. You don't ever want to do that. Okay, so the first step here is going to be, well, we should probably take account of all the atoms. Let's just number these. And again, I'm not numbering this for nomenclature. I'm just numbering it to keep track of it. You can sort of decide your numbering system is going to be whatever it is, but once you do that, you've got to keep it consistent. So the methyl is 1. That methyl is 1. This is not a reduction or an oxidation, right? Carbon 2 here has 2 bonds to an oxygen. Remember, you're paying attention to your neighbor, partner, friends, paper. So carbon 2 has 2 bonds to oxygen. Carbon 2 has 2 bonds to oxygen. 3, 4, 5, 6. 3, 4, 5, 6. 6 is single bonded to an OH on this side. That's going to be this O. So if I put an X on that O, that. And then you might wonder, are these the same OHs? And in fact, it could be, might not be. But the first thing you're going to need to do, like we can make this ring by having this oxygen swing around and attack this carbonyl. Right? So this OH is a weak nucleophile, right? Neutral oxygens are weak nucleophiles. So we could just imagine doing this. Don't mark the paper just yet. We could do that. If we do that, that's what we get. All right. Again, don't mark the paper yet. That's not correct. Actually, do mark the paper. If somebody did that, make a note that it's wrong. So, how do I know that? Actually, and I would get on you guys hard for that. You got to put that second there. So, the first arrow, right? This first arrow I drew and then didn't follow through on, makes a bond between the O that's marked X and carbon 2. That arrow is the only one there, so that's all that would be there. And so, in fact, the way that first arrow I drew would give us this. Right? As it's drawn right now, that's what we get. Is it clear why that's wrong? What's that? It's a Texas carbon. Somebody doesn't like Texas. Do you not like Texas? You're ambivalent about Texas. What is worse, Texas or carbons with five bonds? Good answer. Have you looked at my biography? I'm from Oklahoma, so Texas stuff. I actually once, in an interview at a university in Texas, somebody said something about the great state of Texas, and I said, I'm not so sure Texas is a great state. You'll know that I now work in North Carolina. So don't do that. If you go on a job interview, do not insult your host. So Texas carbon or carbon with 5 bonds. And Alaska carbon is a carbon with 6 bonds. I have another joke, but I can't think. Sorry. All right, so that is wrong. Anytime, and you guys should do this. I've talked a lot. I've seen a bunch of you about the exam. Like, don't change your answers. A lot of you probably have had this experience where you change the answer from the correct to the incorrect. Don't change an answer just because you lack faith in your answer. But if you see something that you know is wrong, right? Like, hey, oh crap, I drew 5 bonds to a carbon. Everybody will do it. I drew this arrow and started talking to you guys, right? I got distracted and I wound up, I didn't draw it, but I have a molecule that's going to have 5 bonds to carbon. It happens. It happens more when you're at the beginning of your organic chemistry career than toward the end. If you go through your paper and you see a carbon with 5 bonds or 6 or 7, change it. Like, draw a molecule that has 4 bonds to carbon. You might not draw the right molecule, but I will see that from a long distance away. Okay, so what you actually need, this oxygen could attack carbon 2. That's going to force electrons up onto the oxygen, and that'll give us what I first drew, which is also wrong, but less obviously wrong. Okay, so that is also wrong. What's wrong with that? Yeah, but what's wrong with that? What's specifically wrong with that structure? It is unstable, but why? So that is one thing, but that does happen, and we can talk a little bit more about acid base. I probably need to do a little more acid base. Certainly, when we get to the means, we'll talk about it. Charge is not always less stable than uncharged. So it can happen that you'd rather have charges than neutral atoms if something else stabilizes. How strong a base is this? Pretty strong base. Localized charge, negative charge on oxygen. How strong an acid is that? Quite. So you've got a strong acid and a strong base. Right? You're never going to have a reaction will never be favored that goes from a weak base and a weak acid to a strong acid and a strong base. Right? Strong acid, strong base always react to make weak acid and base. So this is not right. We can't just immediately do that. All right, so I'm going to erase that now. What would you do first to prevent that? What should be the first thing that happens? Yeah, we're going to protonate the oxygen. So the first thing that happens, that oxygen is going to grab a proton. I'm going to draw this as HA. This is basically AH, right? The thing that is important about paratoluene sulfonic acid is that H. The rest of the molecule is not all that important. So the first thing that happens is the O grabs the proton. We got to break the HA bond again. Just like carbon can't have 5 bonds, a hydrogen can't have 2 bonds. Why didn't I protonate this one? It isn't actually as strong a base as the carbonyl. Right? So, right, we've got the resonance structure here where the pi electrons go up in the oxygen, you get an O minus. The sp2O is a stronger base than the sp3O, but not by much. And in fact, in this reaction, protons probably hop onto the O and then hop back off. I hesitate to mention that because it does confuse the issue. But it's also to explain what a mechanism is. Right? So I do this a lot. I teach Orgo. I make you guys learn mechanisms. I grade them. Everybody's generally kind of dissatisfied by the whole process. A mechanism is not like the whole thing. A mechanism is the route from the starting material to the product. Right? There could be a whole bunch of other stuff going on that doesn't actually get you there. Right? If you go for your med school interview and they ask you like, what's led you to this position? You were not going to tell them about playing t-ball when you were 5, right? Unless you like dislocated your knee or something, and that's when you fell in love with medicine. Right? You're going to tell them a story that takes you from wherever to I want to be a doctor. You don't tell them that you loved friends or whatever. Right? You don't put in unnecessary stuff. So this oxygen can grab a proton. It can hydrogen bond to other stuff, but none of that takes us to the product, so we don't include it in the mechanism. Okay, so from here, what would you do next? You want to deproton. All right, so we have a vote for it's not right. I see a lot. It is a pretty logical thing to do, right? In the product, I said that this oxygen is X. There's that oxygen. It doesn't have an X on it, or it doesn't have a proton on it. Right? So we got to get rid of the proton. So taking the proton off makes sense.
I was trying to say, what if we just use that sulfonic acid as active?
You want to have sulfonic acid attack here.
Yeah.
All right, so let's do that. Do that. So basically, this is going to be the A minus. I'll draw it up.
It would be
So we do have this. This is the A minus. And we have a vote for this. Yeah. I'm just gonna draw that as A. Oh, yeah, no, that's right. That's also wrong. Why? Okay, let's take this in order. What I'm trying to do with today's this exercise, I'm not trying to frustrate you. I'm trying to see like common things people do and how you can try to figure out that it's wrong. So on the first one, deprotonate the alcohol. And I should draw out the base, what the base is. So the base is also gonna have to be, like the only base you have around is that, right? There's nothing else in there that can take that proton off. There has to be a base. So there's two reasons I can find that will not happen. What are they? Right. So if we just look at this as an acid-base equilibrium, right? Localized O minus, highly delocalized O minus. This is the conjugate base of a strong acid. It's going to mean it's a really weak base. This is the conjugate base of a fairly weak acid. So it's going to be a pretty strong base. So we're going from a weak base to a strong base. The equilibrium is not going to favor that. You always have to have a base to pull off a proton, right? You can't just like get rid of the proton. The other thing, and we have the same error that we had up with the first idea, strong base, strong acid in the same mixture, right? So if I did somehow have a base strong enough to pull this proton off, wouldn't pull this proton off, it'd pull that proton off. Again, no, not write your name. When you use an acid, if you're gonna do an acid-base reaction, the first acid-base reaction that will happen is the strongest acid present will react with the strongest base present. So, right, if we have a base, it's going to react with one of these two protons. I mean, theoretically, it could react with the CH protons. CH protons are even less acidic, so none of you are suggesting we pull those protons off. So we have to choose between this one, and that one is more acidic. And that actually, right, I wrote this as an equilibrium. So the carbonyl oxygen grabs a proton from the sulfonic acid. This thing absolutely could just take this proton, go right on, but it won't take that one. And if we had a strong enough base to pull this proton off, we couldn't have protonated here in the first place. Okay, so this doesn't work. What's wrong? Kind of this, is it the same? What's wrong with this one? So I guess what we should do, I can't actually find anything clearly wrong with that one. This is a reasonable structure, right? We've got a bunch of atoms that are negative. So what's the next thing you propose to do?
The next thing I did was take that H off from the O and let it knock down for the top O, and then let it knock down and get A off. So then you will have O minus attack where A is.
So we're going to take this H?
No,
that H.
Yes.
What's going to take that H?
That's a good one.
Yeah. So again, no, that like seriously, that I told you guys not to laugh at it. All right, but that is, you should always, I swear you will want to do this. I do this at work. I'm like, my grant depends on this proton coming off. Therefore, it's got to come off, right? Like, and that's not the way chemistry works. Chemistry works by having a base that is present. If the next thing so this thing is actually, again, this is an equilibrium. The sulfonic acid might add into that carbonate. The problem is it doesn't get you toward the product. So if you wanted to do, there's another problem. Let's just stipulate, let's say we had a base that could take that proton off, all right? There isn't one. Like I said, anytime you guys pull a proton off, you've got to identify what does that and think to yourself, is this a base that could deprotonate this acid? And now what you want to do, I think, is an SN2, tertiary center. All right, that's a sterically hindered position. So the you guys remember this? SN2 reactions don't, like a direct kick out of the tosylate. And honestly, this is a good, I actually like this. All right, so you guys have seen tosylates as leaving groups. So I do actually like what you're thinking there. that, hey, you could do an SN2, you kick that tosylate out. When I say this is something that could happen, it's not something that happens likely. Again, the tosylate is a good leaving group because it's a really weak base, right? So really weak bases are not good nucleophiles. So this is not a particularly good nucleophile. So having it attack the carbonyl, the protonated carbonyl, is not something that's probably going to happen. But if it does, right, you get a tosylate, and it could be a leaving group. The most likely thing to happen in that case, if you get this leaving group, is just that it would leave on its own, and you'd go right back to this cation. Right. So this equilibrium probably happens. This one definitely happens. All right, so I'm going to take this stuff off the board. We're going to start, see if we got any other ideas. All right, so we're here. Anybody come on? Yeah. All right, we got an idea for the alcohol, just as it is. We're not going to pull that proton off, right? OH attacks the carbonyl. Weak nucleophile. Protonated carbonyls are really strong electrophiles, right? It's protonated, it's got a positive charge. To neutralize that positive charge, it wants electrons. And then if I add a bond here, I've got to break a bond on that carbon. You guys saw that first with the SN2 reaction, right? Nucleophile comes in, makes a bond to carbon. You necessarily have to kick out a leaving group, right? You break a single bond. Here, if you want to think about it this way, the leaving group is the pi bond. All right, I've drawn these arrows. I want you now, either on the side or, you should be also grading, you should be looking at your partner's mechanism. But I want you to draw off to the side somewhere. What do you get from these two red arrows?
Yeah, you get that, but there's a positive one.
Right. So that's what you get. So like I said, and let's color these. So we said this one's X. Put a dot in that one. Okay, so coding the two oxygens. When the OH attacks, it's an OH. So there are no arrows here that take this proton off. So that proton comes along with it. And this gives us a strong acid, but remember, we're under strongly acidic conditions. So we can have strong acids. What we can't have is strong bases. So again, acidic conditions, you can make strong acids. Basic conditions, you can make strong bases. But you don't want to have a strong base and strong acid. So then okay, this is correct. This is the next mechanism. We protonate, the first step is we protonate the carbonyl. The neutral oxygen attacks. Kick electrons up on the oxygen. We have the protonated product. How do we get to the product from there? What deprotonated? Right. So, right, we have the sulfonate. Again, you have to, if we take this H away, we can't just have it vanish. One thing I'll see people do is they'll draw this arrow, they'll draw the arrows right, and they'll just not have the H there. Again, that's like I don't want to have that H there, so if I don't draw it, you can ignore it. But something's going to have to take that, and it's a distinct step. And that regenerates our catalyst. Right? So this O grabbing that H regenerates this green catalyst, which I said is catalyst. It's racemic. Why is this reaction? Why do we get a racemic product? Which step?
The nucleophilic attack either side.
Right. The step that sets our stereochemistry, right? This is achiral, that's achiral, that's chiral. The stereochemistry gets set by this oxygen attacking the carbonyl. Carbonyl's flat, there's nothing around it guarding either side, so the nucleophile comes to the front or back. Remember, this oxygen does not attack this carbonyl by like throwing a Hail Mary pass, right? That long arrow is not saying the electrons alone go here. The molecule has to fold up. Bonds have to rotate. So that this oxygen sits either right above it or right below it. Right in front of the carbonyl or right behind it. So this is necessary before we can go there. All these bonds are single bonds, so there's free rotation about them. Like if those were double bonds that were rigid, this cyclization wouldn't work, right? So if we were trying to do this reaction, 1, 2, 3, 4. And if we had this reaction wouldn't work because that double bond has to stay trans. You can't put a trans double bond in a ring, right? That might have been unnecessary addition of complexity. Any questions about this? All right, when you guys are working mechanisms, and I've talked to some of you about this, if you look on the Canvas page, I've got all my 122 like sort of problem sets. There's some resonance stuff, there's some mechanism stuff, some acid-base stuff. All of that would be worthwhile reviewing. Again, you don't have to like do the whole work. They're long work sets, worksheets. You don't have to do them all at once. Work a couple of days, just as a little review. The key is with them, so you can take a look at that. When you work mechanism problems, you should think about it this critically, right? Especially where you guys are. And again, I mean, no insult by that, right? You're just learning this stuff. So, like, ask yourself, I just lost a proton. A base had to take that proton. What base did it? Is that an acid-base reaction that makes sense? So if you would, make sure names are on the sheets, hand them toward the middle. I'm not going to grade these. I might look at them a little bit. But you're here, you're in class, you get credit for this. Need everybody leave. All right. I've been promising chapter 13 for a while. I figured I should actually get around to it. I know you guys are all like, put as many chapters on the exam as possible. If there's any more, just pass them forward as you come to it. So chapter 13 is ethers, epoxides, and sulfur. It's kind of a catch-all chapter. I'm not going to spend a tremendous amount of time in this chapter. They are important functional groups. But teaching functional groups, I would much rather teach mechanism. If you guys will learn what are nucleophiles, what are electrophiles, what are acids, what are bases, you can do most ionic organic chemistry. Like, I'm not saying you'll learn it all overnight, but you could work to understand it. Learning by functional groups is sort of hard, but it's also important. Like, a lot of you are going to end up in a profession where you're kind of tangentially involved with organic chemistry. You need to be able to look at a structure and sort of see some stuff in it. but nobody's gonna ask you to make it, nobody's gonna ask you for detailed structural analysis, you're not gonna look at NMRs or anything. So you need to be able to recognize an ether. The most common ether is just called ether. So ethyl ether or diethyl ether, right? Two ethyl groups. This compound's been known a very, very long time. Like medieval chemists, alchemists discovered this compound. They discovered it by taking ethanol, mixing it with strong acids, usually sulfuric acid, and heating it. Right? That reaction produces diethyl ether. We get ethanol, like humans have been making ethanol as long as, maybe longer than we've been humans. Sulfuric acid you can make pretty easily. So you put those two together, you heat them up, and we get this ether. You guys may have heard of the ether, right? Like something that pervades the universe and stuff. This is where this comes from. And you probably haven't used ether in lab. It's extremely flammable. It's really low, it's very, very volatile. Like its boiling point is actually a little bit below body temperature. So if you have a flask of ether and you want to boil it, you can just like hold the flask. Right? And then the Cheerios do it that morning will boil the ether. And it comes off, you can kind of see these wavy lines and it smells nice. It's actually a good anesthetic, you can get high. And so it's the ether, right? You smell this stuff and like you go to that special place. Anyway, the ether functional group is a carbon, oxygen, carbon, with the stipulation that neither of those carbons can be a carbonyl. Right? If one of the carbons is a carbonyl, that's an ester. Right? Ether and ester. Not only do they look similar, they sound similar, and students confuse them all the time. A little easier is if they're both carbonyls. This is an anhydride. We'll talk about that in chapter 20. The important thing for this chapter is esters and hydrides are not. So the chemistry of an ester very different than the chemistry of an ether. Chemistry of an anhydride way, way different than an ether. Ethers are actually quite robust. They're very stable. They're less stable to acid, but they're still pretty stable to acid. They're extremely stable to base. They're kind of boring inside. Right? So the best way to synthesize them is SN2, SN1, or electrophilic addition. Right? So if we think about this, if I have the conjugate base of propanol and ethyl chloride, I get an SN2 reaction. O kicks out chloride. I get ethyl propyl ether. The nomenclature for these is really simple. Look at the alkyl group on one side, look at the alkyl group on the other side, put those in alphabetical order ahead of the word ether. You can also make these by SN1. I'm not going to go through that mechanism right now, right? But if you have a tertiary center, so a tertiary chloride, the chloride leaves, we get a cation, ethanol attacks, we get T-butyl ethyl ether. And you can make these by electrophilic addition. Right, so you guys might remember electrophilic hydration of an alkene from chapter 8. If you use an alcohol instead of water, you get an ether out of it. And that would be cyclohexylmethyl ether. Sorry to make you guys stand up. Like I said, ethers are quite unreactive except with acid. So So we can cleave these. T-butyl ethers, especially, this is really the only one I'm going to talk about. T-butyl ethers are pretty easy to cleave with acid. I'll go through this mechanism. Again, we're going to protonate something. We got an oxygen. We protonate that. Nope. Sorry, guys. Right, this is just the reverse of making the ether via an SN1. Right, if we protonate this oxygen, now methanol is a good leaving group. So methanol leaves. Get our tertiary cation and methanol. We have some HSO4 minus around. And that can give us the elimination. The book, chapter 13, I put up omitted sections. Yesterday, there's an announcement with omitted sections from the book. I didn't omit these ether sections, but we're not going to hit them very hard, all right? So acid cleavage of an ether really only works if one of the two alkyl groups can come off and be a really stable cation. So if you have diethyl ether, right? Methyl cation or primary cation. Diethyl ether really doesn't, it's very difficult to cleave dimethyl. Methyl ethers are a little easier to cleave. You can coordinate here and have a nucleophile attack. If you can come up with a Lewis acid that has a good nucleophile as well, your book talks about this. You can coordinate the oxygen to a metal. And if you have like a bromide or an iodide or something, that can come in and do an SN2 on the methyl and kick out T-butyl. We're not going to talk about that much. You're going to see in the book, take a look at it. You might see reactions like this on the ACS exam or MCAT, DAT, whatever professional exam you eventually choose to take. But we're not going to do much with that. The one thing I should mention over here on the SN2, or actually all these, all these syntheses, cleavage, synthesis, and this kind of goes without saying, I hope, the reaction has to be reasonable. Right? I say you're going to do an SN2. If this was a tertiary center, you can't make that ether by an SN2, right? You can't do an SN2 on a tertiary carbon. You can't do an SN1 with a primary or a methyl cation. So I'm going to assign you guys some problems for that. It's good SN2, SN1 review. So if you need to review that, do, but I'm not gonna. We'll probably wind up working some problems in class like we just did with the mechanism. All right. Let's talk about epoxides. Epoxides are a lot more interesting. So you guys might remember this reaction. An epoxide, epoxide. I said I'm from Oklahoma, so I have trouble with vowels sometimes. An epoxide is a 3-membered ring that's got an oxygen in it. It's a cyclic ether. All right, I just said, I said ethers are really stable to base and nucleophiles. And they are. Epoxides aren't. Okay, so remember, 3-membered rings of any kind are going to have significant ring strength. Geometry tells us those bond angles are 60 degrees. Molecular orbitals want those bonds to be 109. All right, geometry wins. So the bond angle is closer to 60 than 109.5. The orbitals do weird things to not be exactly 60, and it weakens those bonds. So we can open epoxides with acid and a weak nucleophile. Sorry. So you can open epoxides either under acidic or basic conditions. Epoxides are actually quite reactive because of that ring strength. So I'm going to go through, I'm going to take the epoxide we made up there. And again, I'm just using this one as an example. It can be any epoxide. We'll do this. And you guys might have seen this reaction. Your Orgo 1 instructor might have done this. I do this when we do the alkene reactions. So if you take an epoxide and you expose it to acid, and again, it could be paratoluene sulfonic, it could be sulfuric acid, HCl, it's got to be a strong acid. We're going to end up with, actually, let me do this. Can everybody note that I just added a methyl group? So it's not exactly the reaction we did at the top. Just trying to differentiate the two positions here. All right, so if we expose an epoxide to acid and a weak nucleophile, could be water, could be an alcohol, could be a carboxylic acid, there's a lot of them. We're going to end up with an OH on one carbon and the weak nucleophile on the other carbon. They will be trans or anti. The addition is anti. All right, so it's like a backside attack. Let's go through the mechanism. The mechanism is going to be the epoxide oxygen grabbing a proton. Again, we have to protonate. We have a weak nucleophile. That weak nucleophile is not going to come in and just like boot out whatever. So we got to protonate it to make it a stronger electrophile. And then, sorry. Well, however you want to view this, I always hate teaching this part. Right, we tell you guys that resonance structures have the same connectivity. So the structure on the right would not be a resonance structure of the molecule on the left. What this really is at this point is what we call a 3-center 2-electron bond. You guys can let that drop right out of your heads if you want to. But it's 3 atoms sharing 2 electrons. So there's like 2/3 of a bond sort of between all of these. The upshot of this is, when you're thinking about this, the nucleophile is going to hit the carbon that would be the best cation. Right? So the nucleophile would wind up on the more substituted carbon. Thinking about this like an SN2 reaction, that's not what you'd expect, right? You'd expect the nucleophile to be on the less substituted, the more sterically accessible carbon. But it also is going to do a backside attack. So the weak nucleophile, ROH in this case, is going to do a backside attack on the more sterically hindered position. I think I just chastised you guys earlier about doing SN2s on tertiary positions, and I've just done one, what looks like one. And the reason is there's significant, this structure here has significant character, right? And you can think about that if the OH is above the plane, then the nucleophile is more likely to come from behind. Turns out that happens 100%. And again, as you think about mechanism, keep track of where the H's are. Right, so the nucleophile that's attacking here is protonated, the alcohol or water. We're under acidic conditions, so you can't pull off the ROH proton. You can't have RO minus in here. All right, so under acidic conditions, we're going to open an epoxide by having a weak nucleophile attack a protonated epoxide. Stereochemistry and regiochemistry it looks like a backside attack on the carbon that makes the most stable cation. And this is racemic. Where does the stereochemistry get set? This is sort of a weird question. It's not obvious. The stereochemistry for this reaction happens here. Right? If we have that methyl there, that methyl, the chiral centers get set by adding the oxygen. So when MCPBA attacks the alkene, that's when we set the stereochemistry. So really, like if we had this at 100%, let's say this was 92% EE here, this would end up 92% EE here. Right, so really, I say racemic. I should probably put an X through that. Whatever your stereochemistry is on the epoxide to start with, usually that's going to be racemic. That gets carried through in this reaction. Just like in an SN2 reaction, right? It's always backside attack. If you're leaving groups on a chiral atom, whatever the EE is of that chiral atom, that winds up the EE just inverted in the product. I get special looks when I talk about EE. Good. All right. I know this is going kind of fast. I'm gonna make an important point here in a minute. Well, not really important, but it will be fun. So again, this is MCPBA. MCPBA is a per acid. So metachloro, right? So there's a chlorine meta to the carbonyl, peroxybenzoic acid. So benzoic acid would be CO2H. Peroxybenzoic acid is CO3H. And so I'll use MCPBA, but basically what you guys need to see here is the thing that will make epoxides is a peroxide. So this gets us, and if we do this reaction, this would be racemic. The way it's drawn, this is racemic. Why is it racemic? Achiral starting material, achiral reactant, right? There's nothing in here that's chiral, so the product has to be racemic. Again, this is going to come in at the end. And now we can add a really strong nucleophile. I'm going to give an example with a green region. And then you guys punch that with H+. Now this reaction is driven by the nucleophile. So the cation stability, there are no cations under basic conditions, right? So the nucleophile just up and attacks the epoxide. Weak electrophile, really strong nucleophile. So the methyl just attacks the epoxide. It's going to do a backside attack. So you're going to end up with anti, whatever the nucleophile is, will be anti to the OH. And the nucleophile will end up on the less substituted position, right? So if I'm a nucleophile, I can hit this carbon easier than I can hit this carbon. Yeah. So is that it's like it's basically an SN2. Yeah. That one really is basically an SN2. Yeah. This one over here is kind of a weird one. It's a lot like the electrophilic bromination, where you have that 3-membered ring with a bromine, a positive bromine in it. All right. Gonna need the notes for this one. All right. This reaction produces an epoxide. Right? The way you know it produces an epoxide is you've got a hyperperoxide. That right there is the thing that's actually gonna provide the driving force and the oxygen. The oxygen that's gonna go in the ring is the OH oxygen. So draw me the product of this reaction.
So in the previous one, does the ROH deprotonate that of R?
Here?
Yeah.
Oh yeah. Sorry, if you're wondering how I got rid of this H at the end, another equivalent of ROH, or it could be like that proton had to come from somewhere. Could be the A- that was that.
Okay.
Yeah. It's been 30 minutes yelling at you guys, but you always gotta have a proton to pull that, something to pull that proton off. That I like just don't. I don't even show the last stuff. Good lecture design. If you have the product drawn, ask yourself if it's chiral. Is the product of this reaction chiral? I'm going to come in here. I'm going to draw it, but I'm going to shield some of these. All right, I'm going to show. So is that epoxide, right? It's a epoxidation is a straightforward thing. If you've got a carbon-carbon double bond, an alkene, pi bond disappears, replace that with an O bonded to both carbons. That makes your epoxide. So is this epoxide chiral? Not a trick question. It is. There's a bunch of chiral centers. I got a bunch, 1 and 2. The other thing about an epoxide, like if you think about, like this can't be a wedge and then a dash. Like that oxygen can't be in front of one carbon. It can't be in front of the molecule and in back of the molecule, right? It's got to be on one side or the other of the molecule. That is chiral. What's the EE of that reaction? Is this molecule chiral? It is not. So what's the EE of the product? Got to vote for 0. Any others? Price is Right. There's 0 and there's not 0. So I can't remember if I said this in class. I know I've said it to a couple of people who've come by and talked about the question on the exam. I think I did talk about this in class. Like really acceptable answers to when I ask you what is the percent E? If I don't give you any experimental data like an NMR or an optical rotation or something, the acceptable answers are 0. Like, oh, it's just going to be received. It's also acceptable to maybe say it's exactly the same, right? That would be reasonable. Like it started off 92% E, and it was exactly inversion, so it had to be 92% E. Any other number you cannot provide. What you can say is it would not be 0. Or you might say it's not going to be what it started with. Like if this reaction, say this reaction went kind of SN1 and SN2 like, the SN2 inverts, the SN1 racemizes. So the EE goes down, but it doesn't go all the way to 0. In this case, we take an achiral substance and we produce a chiral substance. So is titanium isopropoxide chiral? Got 4 things on the titanium, 4 identical things. That's not T-butyl hydroperoxide. It's not diethyl tartrate. It is. What does that plus mean? Anybody know? The plus means it rotates plane polarized like clockwise. Tartaric acid is a chiral substance. Diethyl tartrate then is a chiral substance. Tartaric acid is where humanity discovered chirality. Pasteur basically, tartaric acid crystallized. All of one enantiomer would crystallize one way, all the other one would crystallize the other way. When you look through it with a microscope, and you pass polarized light through it, you can see he saw different polarizations. He physically like separated them. This is, if you don't have an iPhone and Netflix, like this is what you do for entertainment. Separate the two. We have plus tartaric acid, minus tartaric acid. Optically active chiral molecules. So here's the thing. This actually comes out, we get this in a 45% yield. You guys can actually look this up. 95% EE. So it's very nearly optically pure. Like this is incredible. And it all comes from this. So in order to go from achiral reagents to an optically active chiral product, something in the mix has to be chiral and optically active. Right? And so what we have tartaric acid or diethyl tartrate, and we only use 1 enantiomer of diethyl tartrate. Right? If we use the racemic mixture of diethyl tartrate, we'd get racemic product. If we don't, you can actually do this reaction you don't need the diethyl tartrate to do the epoxidation. Right? If I mix titanium isopropoxide and T-butyl hydroperoxide, I will get epoxide. I will get the epoxide product. It will just be racemic. Why is this important? Well, now I've functionalized these 2 carbons. I've just shown you how we can add nucleophiles here, we can add nucleophiles there. We can build a bigger, more complicated organic molecule that is optically active. It's pretty cool, right? Nod your head. Yeah, I think this is pretty cool. This is really cool. It's so cool that in like 2001, the principal investigator who discovered this won a Nobel Prize. This is called the Sharpless epoxidation. All right, so here's the way science works. I don't know if I've mentioned in here, if any of you are interested in graduate work in chemistry or biology or physics, probably engineering, maybe psychology, you can get that paid for. All right. Don't be a schlep that goes to med school and pays a lot of money. Get a PhD. They call you doctor. You can fake CPR. Like it's fine. No, if you want to go to graduate school in sciences, you generally don't pay for it. You don't get paid a lot to go. But you don't pay tuition. You get a small stipend to stay alive. So a whole bunch of people worked for Barry Sharpless. right? So you have these labs with like 30 people at a time working in there, grad students, postdocs, undergrads, and they work this out, and then Sharpless wins the Nobel Prize, and everybody will remember him. Anybody know why I'm talking about Sharpless today? I mean, you know, other than chapter 13. Google Sharpless when you leave. Pretty cool story. So that is, I did not mention sulfur. I'm going to mention sulfur. I have 45 seconds. Sulfur, one row down on the periodic table. So all this ether stuff I did over here, sulfur does it too. All right, so like, if that's a sulfur, I'm going to have thioether. Thioethers are real fun names, right? Like, it's an ether, but it's sulfur, so thio. It's a better nucleophile. SHs are stronger acids than OHs. Sulfur is a better nucleophile than oxygen. You can make a thioetoxide. It's a little harder to make, and they are less stable. There's more ring strain. The bonds are weaker. They come off better. We might. Well, I'll work in sulfur. It's more the discussion probably when we do amines in the last bit of the semester. Seriously, Google Sharpless when you have a moment. Those of you who are in my lab will be over there at 2:15. I've got to send you the password. If you're not in my lab, see ya. Oh, last thing. Sorry, I do have a serious announcement. Sorry about that. On Wednesday next, I am going to give you the last 30 minutes of the class. Will be like kind of a longish quiz worksheet, closed book examination sort of thing that does not get graded. So take it as seriously as you want it. But if you want sort of everything we've done up to now, or like right now, I won't include Monday's stuff, be kind of a mock exam. Nobody's getting extra time or anything like that. It's not going to be graded. It's going to be one of the things you turn in. But it will be like 3 questions. So it's about the right length for 30 minutes. You can sort of maybe see where you are. All right. All right. See ya.